Okay, so hi everyone. So today in this video, I will be explaining you the solution for this problem, roads not only in Berland, taken from Codeforces, and this problem is rated 1900, and we will see how we can solve this problem by using the disjoint set union and normal graph theory from whatever we studied till now, right? So the problem reads like this, that Berland government decided to improve relations with neighboring countries. First of all, it was decided to build new roads so that from each city of Berland and neighboring countries it became possible to reach all the others. There are n cities in Berland and neighboring countries in total, and exactly n minus 1 two-way roads. So there are n cities and n minus 1 two-way roads. So we can say that it is like a tree, right? Because of the recent financial crisis, the Berland government is strongly pressed for money. So to build a new road, it has to close some of the existing ones. So every day it is possible to close one existing road and immediately build a new one. Your task is to determine how many days would be needed to rebuild roads so that from each city it became possible to reach all the others, and to draw a plan of closure old roads and building of new ones. So in the input we will be given the integer n, and it can go up to 1000. So the constraint is not very much high in this problem, and this n represents the total number of cities in this country Berland and also the neighboring countries, right? And in the next n minus 1 lines we will be given the description of the roads separated by two integers a and b, right? So a and b will represent a pair of cities connected by a road. It will be bidirectional, and it can't be more than one road between a pair of cities. So between two different cities, two different roads will not be there, right? So only one road will be there for per pair of city, and no road connects the city with itself. Okay, so self looping will not be there. So for this we have to output the t, that is the least amount of days for the given condition to satisfy. What was the given condition? To rebuild roads so that from each city it become possible to reach every other city. And also we have to print t lines. And what will these t lines represent? So it will represent like I, j, u, v, 4 integers. So what does this mean? It means that we have to close the road present between I and j initially, and instead, in place of this ij, we have to build a road between cities u and v, right? So this process will take 1 day. So for this we have to print the minimum amount of days so that it will be possible to reach every city from every other city. And cities are numbered from 1, so whatever the inputs are given, it is given 1 based indexing, right? And also it is written that the answer is not unique. So it is definitely possible for this question that the answer might not be unique. So whatever the output is given here, it might not match from what I will explain, but multiple answers are possible. So yes. So now let's understand with this example in the blackboard to understand better. So let us consider the same example which was given in test case 2 in the question. So for this example you can see that the first city is connected to the second city is connected to the third city, and third city is connected to the first city. Similarly, fourth city is connected to the fifth city is connected to the sixth city, and sixth city is connected to the seventh city. As you can see that n is equal to 7, and total number of edges is equal to 7 minus 1, that is 6. 1 2 3 4 5 6, right? Okay, so let us see why the output for this example is 1 and then 3137. So what was asked in the question? In the question, if you see, then it was asked that ultimately what we want is, we want that we should be able to go from every city to every other city, right? So if you read here, it is clearly written that your task is to determine how many days would be needed to rebuild roads so that from each city it become possible to reach all the others. So initially if you see, then these cities, that is 1 2 3, and then these pair of cities, that is 4 5 6 7, these two are not connected, so there is no way that we can go from the first city to the fourth city or fifth or sixth or seventh. Similarly, we cannot go from the second city to any of these. Similarly, we cannot go from the third city to any of this, and vice versa, right? So we want that these any of these cities must have a link with any of this city. Then only we will be able to travel from this component to this component, right? So for that, what we can do, so since in the question it was allowed that we can construct a edge or a road between two cities and remove an existing one, so what we can do is we will suppose add an edge, that is build a road between the third city and the seventh city. So if you build a road between third city and the seventh city, then at the same time we also have to remove one existing road, right? So if you see now, then we can either remove the road between the first and the second city, or we can remove the road between the second and the third city, or the road between the first and the third city. So whatever edges we are given initially, we can remove any one of them in order to build this blue one, right? So tell me, what edge should we remove so that it will be the most beneficial for us? So suppose I decided to remove this edge, that is fourth and fifth. So if I remove this edge and build this blue one, so now is it possible to reach every city from every other city? No. Why? Because the graph is now divided into two components, right? So we cannot remove this link. Can we remove this link between fifth and sixth? No. Again, the graph will be divided in two separate components, so we cannot remove this. Similarly, we cannot remove this. Now let's try to remove this edge. So now after removing this edge, what is happening? We removed this edge between 1 and 3 and build a new one between 3rd and 7, and now if you see, then it is possible to reach every city from every other city, since the graph is bidirectional obviously. So yes, we can remove this link between the first and the third city and build a new link between 3rd and 7th. So since in the question it was asked us to print the format in this way, like ij u v, that is we have to remove between I and j and print between u and v. So the same thing if we do here, then what we did, we removed the link between this 3 and 1 and added the edge between 3 and 7. That's why it is written 3137. And how many days it took in total? So in total it took only 1 day. Why? Because in the first day we removed the link between 1 and on the same day we added the link between 3 and 7, and in this way the whole graph got connected, and that's why now it is possible to traverse from any other city to every other city, right? So that's why the total number of days that it took, right? So it represents total number of minimum days. So total number of minimum days in order to connect the whole graph, and whatever operation we performed on these days, it is represented by this, right? But since in the question it was given that multiple answers are possible, so let me try to help you with another possible output here, right? So if you remember, then this was the original graph, and earlier we removed the link between 3 and 1 and added between 3 and 7. Now what we can say is, let us now remove the link between 1 and 2. So if we remove the link between 1 and 2 and add a link between let's say 5 and 2, right? 5 and 2. Earlier we did it for 3 and 7, now we are doing it for 5 and 2. Now can you tell me if the whole graph is connected or not? So if you see carefully, then we can reach from 1 then 3, 1 to 3, then 3 to 2, then 2 to 5, 5 to 4, 4 to 5, 5 to 6, 6 to 7. So again the whole graph is connected if we did in this fashion. So again it will take us just 1 day, because we removed one edge and added another edge between these 5 and 2. And what edge we removed? So we removed the 1 and 2. And what edge did we added? So we added the 2 and 5. So this is also a valid output for this example. So let us now look at this example which was given in the problem statement itself. So in this example we have two cities, 1 and 2, and initially an edge is present between 1 and 2. So if you see, then it is possible to go from the first city to the second city and from the second city to the first city, right? So the whole graph or the whole country is kind of connected. Like we do not need to remove any edge, and in place of that we do not need to add any edge, right? Because already the graph is connected. That's why the output for this example is 0, since we do not need to remove any edge, and hence the total number of days would be 0. So I hope you understood these two examples given in the problem statement. So what will be our logic when coding the solution of this problem? So it would be quite simple. So what we will do is, we will kind of keep track of the redundant edges. Like if you see, then after removing the edge between 1 and 2, these 1, 2 and 3 are still connected, right? So we can say that the edge between 1 and 2 is redundant. Similarly, if we have not removed this and instead we have removed the edge between 1 and 3rd city, then we can say that still the first and second and third cities would have remained connected. So in that case, this edge would have been considered as redundant. So if somehow we are able to keep track of all the redundant edges that are present in the given graph, don't you think that we would be able to use those edges to remove them, and instead in place of that adding a new edge, right? And that new edge will be added between two different components, their ultimate parents, because initially they are disconnected and we want to connect them, and to connect them we want to add a new edge, and in to add a new edge we want to remove an existing one, but we don't want to remove in such a way that again the graph becomes disconnected. That's why we will try to remove only that edge upon whose removal the graph remains unaffected, that is, it do not become disconnected again, right? So our very first step would be to keep track of all the redundant edges that are present in this given graph. How we will do this, I will tell you very soon. So this was the original graph that was given in the question, if you remember. So this is the list of edges that was given in this input. So first we were told to connect 1 and 2, then 2 and 3, then 3 and 1, then 4 and 5, then 5 and 6, then 6 and 7. So after connecting all these edges, we were getting this graph, right? So as I told you just before, that we want to keep track of the redundant edges. So how we will keep track of the redundant edges here? See, so suppose I again rebuild the graph from the very scratch. So let me do that for you. So we have to connect a road between first and second cities. So we have connected a road between first and second city. Now we want to connect a road between second and third city. So now if I build a road between second and third city, it's okay, right? But now if I try to build a road between third and first city, so will we want to do this? Because if you see, then the third and the first cities are already connected. That is, it is possible to reach first city from the third city and vice versa. So if we again connect these two cities, don't you think that this edge will be redundant? And we don't need that, because even after adding this, nothing is changing in this graph, right? So this is a redundant edge. So this edge is a redundant edge, and we don't want to add this in our original graph. So I will just erase this, right? And I will mark this as redundant. Now let us continue building the graph. So now we want to connect the fourth and fifth city. Since they are not connected already, so we will connect those for sure. And then we want to connect fifth and sixth city. So again there is no problem because they are not connected. So this edge is not going into west. And then the sixth and the seventh city, like this. So after traversing all the edges given in the input, we saw that we only had one redundant edge, that is the edge between third and the first city. It means that we can use this redundant edge in order to build a pair of road between any two cities. Now we have solved the first step, that is, we now have the track of this redundant edge. So we might store this as a pair in some data structure, say vector of pairs, right? So we will store this somewhere, so it's not an issue. And now our second task is to keep track of the cities that needs to be connected. So now if you see, then we want to connect these two components. Only then it will be possible to reach every city from every other city. So we can either connect 1 and 4, or 1 or 5, or 1 or 6, or 1 or 7, or 2 or 4, 2 5, 2 6, 2 7, or 3 4, 3 5, 3 6, 3 7. So we can connect any one city from this to any city from this, right? So let's suppose we connected the city 3 and 7, that is third from this component and seventh from this component, like this, right? So like this. So as you saw that while connecting these 3 and 7, we had multiple options to connect, like any city from this component to any city from this component. So how we will decide what cities from each component should we connect? So for that I will simply keep track of all the ultimate parents for each component. So suppose for this component, third was my ultimate parent, and for this component, seventh was my ultimate parent. So when I will be using this redundant edge in order to build a new road, I will simply connect the new road between these ultimate parents. So we don't have to decide by ourselves that between what cities we should connect. So we'll directly connect the road between the ultimate parents, because since the ultimate parents are different, it clearly means that these two are present in different components. So we need to connect them for sure. That's why we will connect the ultimate parents. So that's why I will connect this. So now it means that we have to keep track of all the ultimate parents for each component, right? So how we will do this? So we can do this by using a simple traversal in OFN. That is, we will visit each and every node and check for its ultimate parent. If it is equal to itself, then it means that it is the ultimate parent of its component, right? And it will be unique for that component. So suppose for that this component I get 3, and for this component I got 7. So in the similar ways in which we stored this 3 and 1 redundant edge, we will also store this 3 and 7. So I hope you got the concept, like how disjoint set union was useful in this problem, and how we used this to keep track of all the ultimate parents and the redundant edges, right? So let us now try to write the correct code in the editor itself. So this is the given input and this is our expected output. So let me write the code now. So we have to take the input of integer n and then n minus 1 lines. So from I equal to 0 till I equal to n minus 1, and for each of the line I will be taking the input of two cities, say uv, so that we have to build a road between u and v. So as I said that while building the roads, we will only connect these two cities only if they are not connected initially, right? Otherwise we will be adding a redundant edge which we do not want. So the same thing we will do here. So if the ultimate parent, so I think I also have to add the DSU code here, so just a second. And also this is my standard template for the disjoint set union, so I'll be using this only here. And more formally if I speak, then I will be using the union by size instead of union by rank. So now what I will say is, so if the ultimate parent, so I think I also have to declare the disjoint set union here. So I will name it ds and it will be of the size n, and in the this class it will automatically make this of n plus 1 size, so we don't have to worry about the one based indexing in that case. So if the ultimate parent of u is not same as the ultimate parent of v, that is these two cities are not connected, it means that the edge that we are trying to add uv is not a redundant edge, it is a useful edge. So we will connect these two. So ds.union by size, right? ds.union by size u comma v, and if it is not the case, it means that the edge is a redundant one because the two cities are already connected. So in that case I will store this redundant edge. So I will say redundant dot pushback. These I will store it as a pair, say uv, and let me also declare a vector for the same. So here vector of pair, and let's name it as redundant edges, right? So okay, perfect. So now we have the track of all the redundant edges that we wanted in the step 1. And now what we want to keep track of all the ultimate parents of each and every component, right? So for that, just do a simple traversal from the first city till the nth city. So for int I equal to 1, I will go till the last city, and I will just check if the ultimate parent of this city is equal to itself. If it is, then it means that it is the ultimate parent for that component. So I wanted it to store, right? So I will just say that ultimate parents dot push back this I. So in this way, I will also be keeping track of the all the ultimate parents present in each and every component. So let us store this in a vector only. So now we have the track of all the redundant edges and all the ultimate parents that we want to connect for each and every component. So now what the question has asked, if you remember, it wanted us to print the minimum amount of days needed to rebuild the roads, right? Minimum amount of days. And to do this, so if you remember, in the question we were asked to find the least amount of days needed to rebuild the roads, right? Least amount of days. So if you try to look with attention, then it is clearly visible that those minimum number of days will nothing but it will be equal to total number of components minus 1, because since here there are two components, it means that there would be two ultimate parents, and these two ultimate parents would form a one pair. So for every two ultimate parents, we will get a one new road, right? So that's why the minimum amount of days, or rather the minimum number of roads that we need to connect, would be equal to the total number of components minus 1. Because suppose in this example there was another component, let's say 8, right? So to satisfy the problem constraint, what we will have done, suppose it will have been the parent of itself, then we would have connected 8 and 7. So there were 3 components and we used 2 edges to connect all of them. So it would always be equal to the number of components minus 1, that is the number of new roads, and or rather the total number of minimum days that we need to build these new roads. So that's why here, since in the ultimate parents vector we had stored the total number of ultimate parents, so we can say that the whatever the size of this vector is, so its size minus 1 will represent of the thing that I just told you, right? And after printing this, we want to print the details like what edge we removed and what edge we are adding. So for that, I will just iterate through this ultimate parent array only. But I will be iterating not till the last element but last minus 1, because I want a pair of every two ultimate parents that we want to connect, right? So suppose this is the first ultimate parent that we want to connect, so it would be like let me copy this so I don't have to write this again and again. The first ultimate parent would be ultimate parents of I, and the second one would be ultimate parents of I plus 1. So in this way we would be taking every two pairs that we need to connect, right? And also, if you remember, then to connect this F and S we want a redundant edge. So how we will get the redundant edge? So we have stored the redundant edges here, right? So what is this redundant edges? This is a pair, right? So we'll just say pair of intent, let's name it P, and since we can use any of the edge, and as in the example as I just told that we can use any of the redundant edges in order to build a road between any two components, right? So we can use any redundant edge, so we have a freedom to choose any of the redundant edge. So suppose I start picking the redundant edges from the back of this vector, right? So So I will just say redundant edges dot back. So it will give me a pair of consisting of a redundant edge, and after storing this in this p, I will say redundant edges dot pop back, right? So every time we will be picking it from the back only. And so now this p consists of a redundant edge. So let's say we want to remove the first redundant edge, so it would be what? So it would be p dot first. You can also write it as p dot second, so we can write either p dot first or p dot second. So this is the first thing we will remove, and similarly the second thing will be p dot second. So you can exchange these two things, there is no problem. And we just have to print the first things that we were removing, because in the question it was asked that only. So I will be removing this first, and then give a space, and then I will be removing this. So the road, not this, but the road that is present between these two cities. And instead in place of this road, I will be adding a road between this f and s, right? So we'll be adding it between the first and the second, that is the ultimate parent of these two components. So f, right, f and s, right? So in this way I think the code will work fine, and just return a empty return, since this is a void function. Even if you don't write this, there is no problem. Now I think I have written the complete code, and now if I try to run this input example, let's see what happens. Okay, so I think we are getting the correct answer. This might be not matching, but since in the question it was clearly written that multiple answers are possible, so we are removing an edge between 3 and 1, and we are adding an edge between 1 and 4. So now if I try to submit this solution on the Codeforces website, let's see what happens. So now I have submitted the question, and I think it should work. Let's see. Okay, so our answer is accepted, as you can see. So this is the thing that we just wrote. So I really hope that you understood the underlying concept in this problem. Like, I would not say that it is actually a 1900 rated problem, maybe around 1500, but you got the concept, right? Like why disjoint set was essential in this problem, and how it helped us to keep track of the redundant edges, then keeping the ultimate parents, and then connecting them one by one. And since also the constraint was pretty less, like n was going till 1000, so that's why our solution worked very correctly, and I think it was a very optimal solution also. So thank you very much for watching this video, and I will be uploading more and more videos related to disjoint set union in the upcoming days. And don't forget to subscribe this channel. So if you have any suggestions, feel free to write down in the comment section. I will read those comments and act on it accordingly. So yeah, bye.